Did Sam go through yours? Oh yeah, I saw like Abby take a picture of it on Snapchat.
All right, good morning, everyone. So I want to get some announcements out of the way first. So first is no class tomorrow. Tomorrow is PSAT day, so if you're a junior or sophomore, you have the option to take the PSAT tomorrow. So when you come tomorrow, report to your homeroom, your advisement period by 8:15 tomorrow morning. And if there's any adjustments or changes, they will have that at the front of the school. So when you come in to the atrium, you'll be able to make sure you're reporting to the correct classroom. And make sure you bring your calculator. Make sure you bring your pencil. Those things will not be provided for you on the when you get into your classroom, and just be prepared to potentially have to kind of sit and wait from the time that you finish your PSAT until the time that you're being dismissed. It could be anywhere from 30 to 45 minutes. So you can't you can't be on your phone, you can't read a book, you can't do anything. You just have to either sit there or put your head down. So just, yeah, be aware of that. Second thing is that I need to know what if you're rising senior or rising junior. I'd like to know whether you're taking AP Stats or BC Calc. If you're in the classroom, I've already gotten that information, but if you're on Teams, some of you have not gotten back to me. So if you can send me a text remind, let me know whether you want to do Stats or BC Calc. Now, having said that, if you're undecided, still give me one or the other. I want to put something down so that I can have that in by Friday. But if I put something down, it's not set in stone, meaning that you can change your mind later. You're not committed to have to take one or the other, but just to have some things so that they can start building their schedule for next year. Okay. Okay. Any questions? Right. So we're gonna pick up where we left off yesterday. Friday we talked about a second way of dealing with integral problems, and that was with U substitution. And but having said that, we need to understand that U substitution is not the first option when we see an integral problem in front of us. And that's part of the challenge with solving integrals by hand, is knowing which method to use. We're going to be learning as many as 5 to 7 different ways of finding indefinite integrals, and that can kind of get students' head spinning because like looking at a problem, how do you know which method to use? And so I want to start building our foundation and building the order that we want to go down our checklist. Okay, so there's a checklist. Eventually, I'll share what that full checklist is. But for now, there's only two things on that checklist, which is we always want to explore, can I just rely on power rule, moving terms around and getting it ready using my conditions? So that's always option one. If that option fails, either because the problem is too complex for that to happen, or you can't do it because order of operations prevents you from doing it, then you look at your second option, which is U substitution. Okay. So even though there are as many as 5 to 7 methods, the good news is that majority of your problems are going to fall within these two categories of power rule and U substitution. Okay. So that's the good news. But we still need to be able to go down that checklist for sometimes the more obscure type problems may show up. We need to be able to recognize it if these two options don't get us there. But we're going to be kind of using these two options at least for the remainder of this chapter, and also for parts of chapter 5 as well. But we're going to start inserting these less used methods or solutions for specific types of problems when we get into chapter 5 and 6. Okay. So it's important that we consider option number 1 first, because what happens is if you look at example 6, this is one where it's kind of disguised as a U substitution problem because you see parentheses, you see denominator, you see radical, and it just feels like it's maybe a U substitution problem. But if you look at this problem more carefully, you realize that this is really not that messy, right? The radical can be rewritten as y to the 1/2. That y to the 1/2 can be brought up. We can distribute it through, and we rely purely just on power rule conditions to get to the point where we can find the antiderivative, which use power rule. So it's important that we consider power rule conditions first, because if you try to go through U substitution, you're going to end up not being able to make much progress. So I think part of the issue is sometimes we skip this first option, we go into the second one, and it's frustrating going through U substitution. You're trying every U value that you can to get it to work, and nothing works. And the reason why is because we skipped over option number 1, which is just expanding power rule. Okay, so those are the two things I want to start to kind of build as we for our foundational steps for these types of problems. But we did kind of have problems where, like example 7, we ended with this on Friday, where we recognized the first option did not quite work out. We were not able to expand these terms because we can't distribute something through a radical if there are multiple terms added inside that radical. So we had to resort to our second option, which is U substitution. But as we make our substitution, we realize that there are some issues that we're going to have to face, right? This relationship is not going to work out as nicely as we would like. If this was x squared plus 3, then that degree would be perfect because then we get that x to cancel out. But this is one of those problems where we're bracing ourselves for additional steps because that x is not going to go away on its own. So after we make our U substitution, this is kind of like option 2B, where U substitution alone is not going to quite get us there. We got to go through a second set of substitution, and we call that change of variable. And that is, we got to find a clever way to get that x to be replaced. So we look at our assigned equation between u and x. We rearrange it, solve it for x, get our expression in terms of u, and then we distribute, go through power rule, and then we bring our answer back in terms of x. So it's U substitution with some additional steps. Okay. So any questions about number 7 from last Friday? Okay, let's look at example 8. So just to get some more practice with this type of problem, but then going down our checklist to convince ourselves that is the way that we want to approach it. Okay, so here's example 8. Okay, here we go. Okay, first things first. We see an integral problem. We gotta ask ourselves, can I just rely on simple rules here? Can I expand, distribute, and just go through power rule? What do you guys think? X squared, square root of 2 minus x. Can I just distribute that x squared through and rely on just expansion? No, right? Order of operations, just like example 7, right? I can't distribute that now. If it was only a square root of x inside the radical, then yeah, that's fine. We can add exponents, but this is kind of stuck the way it is. We can cross this off our list. We got to go down the path of potentially U substitution. But if I want to do U substitution, I want to see a set of parentheses, right? So I'm going to rewrite this problem. And I'm going to underline the parts, highlight the parts that I'm going to initially replace. Find the derivative, du dx equals -1. Du is equal to -1 dx. I solve for dx, move the -1 over to the other side. Now, if we look at how this is set up, we're understanding that there's going to be some issues ahead, right? The degree inside the for our u value is not going to be a good fit, at least for what we want to happen, right? We want the x to go away, but this degree is not even as high as x squared, so there's no chance, right? It would be perfect if it was 2 minus x cubed, right? Then it would be an easy problem to solve, but we know that we're going to be dealing with that x squared as an issue. Okay, let me make the initial substitutions here. I'm just going to replace the parentheses and the dx, but the x squared, I haven't resolved it yet, so I'm going to keep bringing it down. So with U substitution, our initial goal is to convert everything in terms of U. So we're only a portion of the way there. We still got to deal with this x squared issue. So it didn't go away on its own with our initial U substitution. So what can we do? What's available to us to help us replace that x squared? Yeah, let's solve for x, right? And you may be thinking to yourself, well, if I solve for x, that's not x squared, right? But we can still just think of it as a separate thing, right? We can replace the x and still have that exponent there. So even though we don't have a replacement for x squared, we do have a replacement for x. So if I solve for x, I get x is equal to 2 minus u. So there's our key to the next step here. We're going to take this 2 minus u and insert it in for this x, but let's not forget about that squared, right? That squared is still part of my process here. So here's my next step. All right, any questions so far? So we've addressed our first hurdle. All right, we got into everything in terms of u. That's great, but we're still not ready for our calculus portion. Okay, we're still not ready for power rule because we got to do what before power rule? Yeah, we got to get those exponents. We got to resolve all these issues, right? Basically, it's just the expansion. We got to deal with the parentheses. We got to deal with the squared. Everything's got to be separated nicely. So that's what we're going to be working towards. I'm going to rewrite the problem here. You don't have to, but I like to visually, I like to have my single term ahead of my parentheses. I'm going to resolve this parentheses first. I'm going to FOIL that 2 minus u out first. But even after I FOIL or expand, I still want to leave my result in a set of parentheses because I still need to distribute that term through. So if I expanded this out, I get 4 minus 4u plus u squared. Okay, distribute the u to the 1/2 through. Now, when we distribute, make sure, right, we're adding exponents. One plus 1/2 is 3/2. 2 plus 1/2 is 5/2. And now we should be ready. Now we're everything is resolved, right? Denominator, no issue. Radicals, no issue. Parentheses, no issue. Okay, so now we can do power rule, right? Add 1 to the exponent divided by that new exponent. Complex fractions, we're going to flip them up. Flip them and bring them to the top. So we have our antiderivative, we have the plus c, so everything is nice and clean, right? Is this our final answer? Right, so make sure that when you go through U substitution, that you bring everything back in terms of x. Now, we'll say that this is, if you don't do that, I will consider like a relatively minor issue. You'll lose some points, but the majority you've basically solved the problem. You've done all the hard parts. But I do see a lot of students forgetting to bring the u back in terms of x. So just keep reminding yourselves that u is a temporary variable, that it's there to help us through the process. But then in the end, right, we started with x, so we need to end with x as well. So there's our substitution, right? So u gets replaced with 2 minus x. Okay, any questions with 8? Yes. Oh, right. Yeah, I lost track of that negative. Let me correct that. Thank you. Yeah, so this negative, I just inadvertently changed that to a positive there. Thanks for the catch. Any questions? All right, so this entire process is going to be helpful for today because today we're talking about definite integrals, which is just really adding an additional step to this. Right, so when we talk about definite integrals, we're still going to go through this process, but then we're just going to tack on the fact that we got to evaluate the bounds at the very end, right? So we go plug in the upper and lower bound. So really just one additional step past this. But having said that, we do have two different ways of evaluating our bounds with U substitution problems. Okay, so we'll talk about those two ways today. And then when we get through that, we'll go over even and odd functions. That's our second topic for today. Okay, no questions here. Are we good with fate? Okay, so today we're just going to be tacking on an additional step, but we're going to be experiencing the same thing at the beginning of these next problems. Okay. Moving into U substitution for definite integrals. Okay, so let's look at example 1. The difference here, obviously, is that the bounds, we have bounds in this problem. Okay. So careful with bounds, because I do see a lot of students want to just evaluate the bounds with the expression they see in front of them. But if you plug the bounds into the expression, you're getting a bunch of ordered pairs. You're not going to get what we really want, which is the area under this graph. So we got to keep telling ourselves that we have to find an area formula first before we can work in the bounds. Right? So we have to ignore the bounds. Maybe it's helpful. If you see a definite integral, rewrite it as an indefinite integral. All right, remind yourself, I got to solve this problem first before I do anything with the bounds. I do understand why students want to plug the bounds in first, because we read from left to right. Those are the first numbers we see, and we want to work in those numbers we initially see. So it just feels very natural to take those bounds and plug it in. But we have to remember that's actually the last thing that we do. We don't touch the bounds until we reached a certain point in the problem. Okay, so I'm just going to ignore this. Just going to focus on this here. So 2x, x squared minus 2 to the third power. All right, let's go down our checklist, right? There's only two things right now on our checklist. Power rule. Can I do power rule with this problem? Say it again? No. Okay, so technically, could we do it? Okay, good. Technically, we could do it, but just as a reminder, that on the AP exam as well, if it's anything higher than a 2, then we want to explore something else. It wouldn't be wrong if you fold it out, but we have a more efficient way of working through it. Okay, so yeah, anything that is higher than 2, we don't want to do. And obviously, if it's order of operation issues, then we would stop as well. Okay, but it's important that we practice and make ourselves force ourselves to consider option 1 before we jump into option 2. Okay, so always do option 1 in your head. Okay, so expansion, not ideal. Let's look at our second option, which is U substitution. U substitution, we want to identify the U value. We want to look for a set of parentheses. Parentheses is already here for us, so we don't have to rewrite it. We can just pull it directly from our problem. Okay, so begin our process here. Now look at this problem here. Is this going to be a nice problem for us? Is this going to be an easier U substitution problem for us? Yeah, when you see that relationship, you know that, okay, this is going to work out nicely. We don't have to do any additional steps beyond. So this is nice to see, right? We're expecting the x's to go away. We can jump directly into antiderivative. We don't have to do a lot of cleanup like the previous problem. Okay, so it's good to see that relationship there. Okay, du dx. Okay, we find the derivative, x squared becomes 2x, cross multiply. Divide both sides by 2x. Let's make our round of substitution. I'm only going to replace what I underlined. Whatever I did not underline, I'm going to bring that down. I haven't resolved that yet. Parentheses gets replaced. Don't forget about the exponent though, right? U cubed. And dx becomes, okay, what do we see? Perfectly cancels out. But the important thing was that we needed the what to cancel out. The x's, right? That's what's most important. It's nice that the coefficients cancels out, right? But that's not a deal breaker, right? If the coefficients don't cancel out, we just have to make sure we pull it out in front, we keep track of it, and then at the end we incorporate it back into our answer. But it does, but if it cancels out, great. It'll make our problem a little cleaner. But the important thing is the x's have to go away. If the x's don't go away, either we went down the wrong path, or we have to do some additional work, like change a variable to get that x to be replaced. But looks like we're staring at a relatively easier problem here. Everything is set up nicely for power rule. There's no issues here. We're ready to go. So u to the third becomes what? Okay, good. Add 1 to the exponent divided by that exponent. You can pull that 4 out in front, or you can put it below. So this is basically our antiderivative, right? I'm going to put a bracket here because I'm going to think about starting to evaluate my bounds. But this is where we have kind of diverging methods, okay? And I want us to be familiar with both methods, but ultimately you can decide which method you want to use on the test, okay? Okay, so here's the first method. First method is where we integrate in terms of u. Okay, so in terms of u. But there's an issue that we're staring at right now is, can I use these bounds that I have with this antiderivative that I have in front of me?
Not yet.
Not yet. What's the issue?
The U.
Okay, more specifically. Okay, we need to have compatible variables, right? This is in terms of x, the bounds are in terms of x, but my antiderivative is in terms of u. Either we get everything in terms of x, or we get everything in terms of u. So those are the two methods, right? You can decide which way you want to do it, and I'll show both ways. But first way, we're going to get in terms of u, which means that we're going to leave this alone, but we have to find a way to convert the bounds. So we're going to convert the bounds to be in terms of u. Okay. Do you see something that is available to us to help us convert from one to the other? Good. Yeah, this is our conversion. Just like how we used it for change of variable, that is also how we're going, that's also the key to help move us forward here. So I'm going to say, I'm going to start with lower bounds, since if x equals to 1, right, and I know that u is equal to x squared minus 2, I'm going to make that substitution. Put 1 in for x. So u equals -1. So my lower bound in terms of x has now been converted to a lower bound in terms of u. So I'll transfer this over to the lower bound. Now I have matching variables. That's what I need to be. Okay. Next, x equals 2. Four minus 2 is 2. It just so happens that when we push it through the conversion, it still ends up being the same value. Okay, but we did the conversion. We have our new upper bound. Okay, questions so far? Everybody good? Okay, we're now ready to find the antiderivative. Oh, there's a side note that I want to make here is that whatever, okay, you may come across a situation where your lower bound value all of a sudden becomes higher, and that kind of throws students off. They're looking at it going, well, it started as my lower bound, and all of a sudden it became a higher value. What do I do? So if that happens, just place whatever starts as your lower bound, just blindly place that value in the lower bound position, okay? Don't swap it. Whatever's upper bound, if that upper bound value ends up being smaller, put it in that upper bound location, okay? Now, it may seem strange having the bounds out of place, but that's the way the problem is designed, and everything will work out in the end, okay? But if after doing that step, if you still feel like that you would prefer that upper bound being the higher value, then if you really, really want to, you can flip the bounds and then pull a negative outside, okay? But what I don't want us to do is I don't want us to be just changing the order of the upper and lower bound, without making adjustments, okay? So don't be worried if the lower bound ends up being a larger value than your new upper bound, okay? Just place them where they belong, and things will work out. All right, so everything's in terms of U. We're ready to go. Upper bound gets evaluated first, so 2 plugs in for the U. Lower bound next. Okay, we get 16 over 4 minus 1 over 4. So we have our answer. This answer is related to the area between the graph and the x-axis. There's our definite integral value. Okay, any questions? That's first method. Okay, there's a second method, and the second method you can imagine is going to be in terms of x, right? So that means I'm not gonna stop here with my antiderivative. I'm gonna bring that u in terms of x. So there's my conversion again. Replace the u in terms of x. And once I have my antiderivative in terms of x, then I'm free to use my original bounds, because my original bounds is already in terms of x. So evaluate. 2 plugs in for x. Got 4 minus 2, which is 2. 2 to the 4th is 16. 16 over 4. 1 minus 2 is negative 1. Negative 1 to the 4th is 1/4. So we get the same answer, but we went down to slightly different paths. Okay, any questions with either method? Okay, so on the test, if you come across a problem like this, you can choose which method that you want to use. Okay, but let me talk about pros and cons of each method here. A good thing about the first method is that you are kind of separating the calculations into smaller steps. So when you get to the end, you're staring at a relatively clean problem, and you don't have to deal with a lot of calculations all in one step, because you've taken care of some of the calculations at the front end of the problem. So that's one positive. You don't do all the calculations all at once. You're kind of splitting up into smaller parts. Another good thing about this is that it's important that we have knowledge of this method, okay? Because AP exam, multiple choice, a lot of times they're going to be able to design a problem, and I'll show you when we get to review. They can design a problem which test students if they have the knowledge of this converting bounds and making substitution in terms of U. So it's important that even if you choose that you want to use method 2 for the test or moving forward, we need to have knowledge of this. Okay, so that's why this method is important. The negative of this method is having to go through this additional step, right? Having to this feels like something new. Having to do that additional step, even if the calculation is easier at the back end, it does feel like an additional step that doesn't feel as natural as just getting everything in terms of x. So that is one deterrent why students prefer method 2. Method 2 just feels like it's a natural progression of problems, right? We find the antiderivative. I kept saying that u variable is a temporary variable. So if you bring everything in terms of x, you just plug in the bounds from there. No need to do any conversion. And so that's a nice feature. It just feels like a very natural flow of the problem. But the negative is that you're doing all the calculations at once at the end. You got to keep track of multiple things within the same expression. So that can be a little cumbersome, but that's just the negative of this method. Ideally, you have knowledge of both methods, and you can interchange between the two of them depending on which one you feel more comfortable for certain problems. Maybe option 1 is cleaner for some certain problems. Option 2 is a little cleaner. Okay, any questions there? Yeah.
Will we ever end up in a situation where exponent stuff in this equation is to the 4? Is it ever going to be like some crazy high number there?
Oh, I got you. So the nice thing is that if it's like a really messy number, like raised to the 27th power, you can leave your answer unsimplified and they'll give you full credit. So on the AP exam, if it's free response and if it's non-calculator, you can leave your answer unsimplified. So technically I can leave my answer like this and you'll get full credit. So as long as you have an equivalent answer. In fact, I think I said this last semester as well. When we get to reviewing for AP exams, I'm going to encourage students to not simplify. Leave your answer a mess. It's not ideal for AP graders, but I mean, you save time, and I think that's the best way of working through it. Because if you make a mistake simplifying something, you'll get points taken off. So might as well just save time, leave your answer, and move on to something else. Okay, good. That's a good question there. I do want to point out that there's only 2 methods for this. Unfortunately, a lot of students want to choose method 3, which is plugging in this x variable into this u antiderivative. So that is the most common mistake that I see. They get to this point and they just plug the bounds 1 and 2 in for u to the 4th over 4. So do not do option 3. Choose between one of these 2 options. Everything is in terms of x or everything in terms of u, but don't mismatch the 2 variables. Okay. I'm going to skip example 2. Example 2, I think, ends up being a little bit more involved than what I want to do this year. This is a problem where you go through U substitution, you got to go through a change of variable, and then you have to work in the bounds. So I won't give you one like this on the test. So I'll be happy if for change of variable, if you understand this type of problem, that'll be good. Okay, let's talk about even and odd functions. So this is a last topic for the day. I'm going to skip the review, and I want to talk about the even and odd rules here. Okay, if you can write this down here. So even function, I want to just kind of give a verbal and also a visual description of even functions. Even functions, imagine it as a mirror image on either side of the y-axis. So imagine you can look at a graph, you can fold the graph over the y-axis, and you get the 2 parts to match up perfectly. You get perfect overlap between the folded piece of paper. And that's what an even function is. If you can imagine yourself folding the graph over the y-axis and you get a perfect overlap, you know you're staring at an even function. So let's say we have a graph that looked like this. If you have a perfect overlap, what that means is that your area region is also going to be the split in half. So let's say this region has the area of 2, then we know the second region, the other region must also have an area of 2. Okay, so that's an example. All this property says is that the full region is going to be the same as if I duplicated half of it. So 2 times 2 is 4, and that's the same thing as 2 plus 2. Okay, now odd functions, think of it as equal but opposite values on either side of the y-axis. And another way to think about this is that assuming that you're adding the values of the same distance away from the y-axis, you're going to get the values will zero out. So let me draw a graph. Again, let's say we're going from negative a to a. And let's say a region shows an area of 3. Then if it's a true odd function, I know the other side is going to display a negative 3. And if I add the two values from negative a to a, because they're the same distance away from the y-axis, negative 3 plus 3 is 0. Right. So taking knowledge of that, we're going to look at example 3. So example 3, we're going to be, the problem is going to tell us whether it's an even or odd function. And what's going to happen is they'll give us, the problem will provide for us properties, but the properties provided is not going to be the full picture. So we're going to take those properties and we're going to fill out the remaining gaps in the graph using our knowledge of even versus odd functions. And once we filled out the gaps, then we can total up the values that they're asking us to total. So we have two properties here. The region from 0 to 3 is going to display 2. And then the region from negative 4 to negative 3 is going to display an area of 4. Okay. Now I have more specific ways of going about this, but right now we'll just do the basics and I'll talk about more specifics for more involved problems. Okay, but for now I'm just going to sketch this graph, right? So from 0 to 3, I want to create a region of positive 2. Between negative 4 and negative 3, I'm going to create a region of positive 4. All right, now I know I'm dealing with an even function here, so how can I fill in those remaining gaps? What do I know about this region? Negative 3 to 0 is going to be what? But even, right? Even. So I want a mirror image on both sides. Yep. So positive 2 on this side. Okay. What about from 3 to 4? Also be 4, right? So whatever you see on one side, you're going to duplicate that on the other side. If I multiply all those numbers by 2, I'm going to get the total sum from one end to the other end. All right, good. Any questions? So now we're going to find the integral from negative 4 to 3. Now, careful. Sometimes I see where students assume that they're just going to add up all the numbers because those numbers are all there on the graph. But pay attention, right? We're only adding the values. We got to pay attention to the bounds of our integral here. The problem is only concerned about the interval from negative 4 to 3. So it's not going to be the entire region, right? It's just going to be these numbers here. So 4 plus 2 plus 2. questions there? All right, example 4, it says same as example 3, but a slight change is that now we want this graph to display properties of an odd function. So I'm still going to plot these properties down. 0 to 3, I still want positive 2. Negative 4 to negative 3, I still want a positive 4. But it's an odd function now, so what adjustment do we have to make if I want to fill in these gaps? What's going to go from negative 3 to 0?
Negative.
Yeah, we want equal but opposite, right? So whatever we see on this side, we're going to make it equal, but we're going to make it a different sign. So this side is above, so this side we want below. Okay. What about from 3 to 4? Yeah, opposite sign. Doesn't mean it's always negative. It just means that we always want it to be the opposite of what we see on the other side. To double check that you have your graph correct, you can count up those values. If I go from negative 4 to 4, if I'm looking at the same distance on either side of the y-axis, I should zero out. And if I add up all those numbers, I get 0. Same thing, if I go from negative 3 to 3, I also get 0. So we know that we'll get that 0 out relationship there, or that property there. Okay, so now we'll find the definite integral from negative 4 to 3 of g of x dx. We're again just adding up what the problem has given us, right? We don't want to be adding more than our bounds. So we're only starting from negative 4 and going to 3. We're not looking at that region from 3 to 4. So 4 minus 2 plus 2 is 4. Okay, questions? Now these were not difficult, right? But sometimes the more difficult problems are the ones where they give you properties and those properties end up has some overlapping information, and trying to decipher that can be a little challenging. So I want to kind of give some steps where I feel like if you follow these steps, you won't get thrown off by those overlapping information. Okay, so here are the steps for kind of the more involved problems. First thing is you want to sketch out your smaller interval region first. Interval region. Okay, that helps a lot. Okay, now doesn't mean that the smaller region is going to be a smaller area. We don't really care about the size of the area or how large that value is, but we want to pick the shorter interval. Okay, the shorter interval is going to be a way that we can build out information. Okay, so that's key. Second step is go ahead, once you have that smaller interval filled out, fill out the other side. If it's an odd function, you know what to do on the other side. If it's an even function, you know what. So go ahead and fill out the even odd properties. After you've taken care of everything you can do with your smaller interval, now move on to your larger interval. Okay, so next you're going to use the larger interval. okay, to fill in the remaining gaps. Okay, let me show you what that looks like. Okay, so example 5, we're back to even function. We're given two intervals here. We have the region from 3 to 6 is 7. Interval from -6 to 3 is 12. Okay, which interval do we want to tackle first? From 3 to 6 or from -6 to 3? 3 to 6. Now, don't look at these numbers. I know the 7 is smaller than 12, and so maybe you're thinking, I want to take care of the 7 first. That doesn't matter. This could be 17, this could be 12. We still want to choose 3 to 6. Okay, so smaller interval first, right? 3 to 6 is a lot smaller interval from -6 to 3, right? That spans across 9 units. This is only 3 units. Okay, so smaller interval first. Don't look at the area. Okay, I'll call that 7. Before we move on to the second interval, let's see what we can do with that information. If I know this region is 7, what do I know about the other side? Yeah, also 7, right? Because we're dealing with an even function. So this is important. If you can do this, you won't get lost trying to figure out what to do with that last part. Okay, good so far? Now, the challenging thing about this last piece is -6 to 3. I think a lot of students, when they see this, they want to put something over this and put a 12, right? They want to do this. They want to put all this and just call it 12. But what I want to stress is that you've created something that's set in stone, okay? Nothing is going to be removed. Nothing's going to be added. We're not adding anything to the space. This is set, okay? All we care about is we want to fill in the remaining gaps. And the way we fill in the gaps is we're going to use this information to help us out. So I know from -6 to 3, I want this entire region to add up to be 12. This is already complete. I already have 7 here. All I care about is how can I fill in this space to make this a true statement? Put 5. Okay, it's an even function, so I know I can split that in half. I know I want this region to be 5. But it's an even function, so how can I split that up even further? 2.5. So if you go through these steps, if you go through this logic, you won't get thrown off. But if you don't follow these steps, then you're going to be stuck going, wait, this interval is 12, this interval is 7, how do I resolve that, right? But if you follow the step, it'll be nice and clean, and you want to deal with any messy logic. All right, so this is ready for us to evaluate. We only care about the integral from 0 to 6. Okay, we'll practice with this type of problem as we get closer to test time as well, but want to at least spell that out. Okay, so from 0 to 6, we only care about these numbers here, right? So 2.5 plus 7. .5. All right, any questions? Okay, sorry I went over a little bit, but no class tomorrow. Help session this afternoon at 3:30. If you please get back to me about what you want to take next year, either calc or stats. If you're unsure, just pick one, and then you can always change it later. Have a great day, guys. See you Wednesday.